Okay, here we go team, part 2 of control circuits. So let's have a look, where are we at? We got to control circuit voltages. So any control circuit voltage may be chosen provided the voltage value meets the following conditions. It does not create an electrical hazard, it is within the insulation limits, and is compatible with the components such as contactor or relay coil operating voltages. Typical DC voltage used are 5, 10, 12, 24, 50, 110, 230 and 400 volt. DC values are also used, but economy or ceiling resistors are required connected in series with the coils. These resistors are connected automatically when the contactor is operated. Motor starters have either 230 volt or 400 volt AC coils. Yeah, so what we're talking about here is that if I'm switching a motor, for example, a 230 volt motor, let's say, so the contactor contacts will have 230 volts AC on them, but that doesn't necessarily mean that the coil voltage that is switching that needs to also be 230 volts. It could be 12 volts, it could be 24 volts, it could be any one of the numbers that we have showing here. My laser pointer, here we go. These ones here, 5, 10, 12, 24, 50, 110, whatever. What are the advantages and disadvantages? Well, the advantages of using a lower voltage, a 12 or a 24 volt control circuit to switch my 230 volt or maybe even 400 volt power circuit is that, you know, less danger, less hazards. I don't need that high voltage for my switching circuit. I don't need it for my control circuit. I can use lower voltage if I want to. And then all the components can be lower rated, etc, etc. That's real nice, right? If we think about, again, that example of the emergency stop circuit in 402, I could make all the controls on that 12 volts and then have a 12 volt coil switching my contactor, which is switching the 230 volt sockets, but it doesn't have to be 230 volts on that coil. That means that all those stop buttons, all the start and stop buttons, well, mainly the stop buttons at the desks, could all be 12 volts if I wanted them to. So if I'm in there with a class full of students and they're Gumbies like they are, and they want to get in there and play with stuff and lick the wires, then they're not going to die because it's only 12 volts. Yeah, that's nice. That's nice, right? What are the disadvantages? Well, the disadvantages then, I have a mixed voltage system. So first I have to find a source of 12 volts or 24 volts. It means I need a transformer in there to come off my 230 volt supply. To give me the 12 or 24 volts that I want to use in my control circuit. So there's an extra component in there that I wouldn't otherwise use, and it may get confusing for someone if they're not sure what's going on. That may confuse them that they're seeing two different voltages, 230 volts on the contactor contacts, and let's say 12 volts on the contactor coil. If you're smart, if you're a good sparky who knows what they're doing, then that's not going to confuse you. You'll look at it and go, oh, this must be a 12 volt coil, and then you have a look at the contactor and it'll say on the side 12 volt coil, and okay, sweet. But you never know, there's plenty of dumb sparkies out there, promise you. Alright, push button control. Okay, what do we have here? We have a push button. This is a very simple circuit, a push button. We have a phase positive on this side, positive or phase, negative on this side. Push button there, relay coil. I push the button, coil is energized. That will turn on my contactor. As soon as I release the button, power turns off, coil turns off. Okay, how useful is that? Hard to say. Doesn't seem terribly useful, does it? If I had some sort of control that only wanted momentary power, as in push button, power on, let go, power off, then this is useful. You might see that on some sort of like garage roller doors or something like that, and you push and hold it and it goes up, and then you push and hold and it goes down. As soon as I take my finger off, it stops. Something where you've got to, what's the word? I've forgotten the word that you use, but I push and it moves incrementally along. I would use it like that. It's not very common. Normally we want push button, stays on, push stop, goes off. And this is what we have here, a start-stop control. So this is by miles the most common control. What I'd like you to do is have a look at the slideshow, pause this video if you need to, and pay attention. Have a good look at this diagram here and really absorb it and figure out what's going on, because this is the bread and butter of control circuits. What do we have here? Phase, power comes here, start switch is open, hold contact is open, no power is being transferred. As soon as I push that button down, I'm going to push it once momentarily, and it's going to go through the stop switch is on, that's the normal position, through my relay coil. Relay coil energizes, brings in this hold contact. Once that hold contact is in, then I can let go of the start button and my power will continue through here, and keep the coil in, which means the thing will hold itself on. It stays on until I push the stop button. Once I push the stop button, relay coil turns off, hold contact opens, and therefore no power is going through. Now the start button's open, the hold contact is open, no power is going to the relay coil, everything turns off. Cool. Pretty simple circuit, neat idea. Push the start, turns on, push the stop, turns off. What does it do? It provides the last sentence there, provides no volt protection for motor starters, or what does it say at the top there? Fail safe in the event of a bad connection or broken wire, or no volts. So if something stops, if a wire falls off the stop switch, the whole thing's going to stop. If power goes off, we're using this to control processes in a factory. If power goes off, then when the power comes back on, it's going to require somebody to push that start button before it will start again. What it means is that if power goes on by itself after a couple of hours, then we don't need to worry about somebody having pushed the stop buttons. The machines aren't all going to start up again by themselves. Once the power goes off, everything will stay off until somebody pushes that start again. This is the operation of the start-stop button, which I've just described. Obviously, I will go through these slides as fast as I need to. You can open the slideshow and reread them yourselves, but that's just the operation I've already described. Relay contacts. Small multiple contacts for control relays have contacts made of either gold for low current operation or more commonly silver for general circuits. Gold has the advantage that oxides do not build up on the contact surface. If you remember right back to like our very first module when we talked about gold and silver, and we learned that silver is actually a better conductor than gold, but gold is more commonly used than silver, even though it's more expensive. We have gold contacts in cell phones and electronics and stuff, and the reason is for this, because the gold is more corrosive, resistance to corrosion and oxides. So the circuit diagram here, so it's a changeover arrangement for forward and reverse, right? So it's changeover, it's either one way or the other, forward and reverse. Contactor contacts, main contacts of a contactor switch, relatively high currents. Therefore, silver alone is not adequate for the main contacts because of its softness and low melting point. To solve this problem, alloys of metals like tungsten, silver nickel, or silver cadmium oxide are used to meet the various duty categories. Contactor auxiliary contacts are usually silver. So the auxiliary contacts, I mentioned this I think yesterday in one of the videos, that the auxiliary contacts tend to be a lower operating current than the main contacts. So we can use silver on those because they're not carrying as much current. But on the main power contacts, that's where we're going to be switching our high current. So now high current terminals, we need more corrosion resistant or more high current capability. So silver by itself is not ideal. And the other thing that we need to be aware of with our high contact coils is the fact that we will have arcing in them. Arcing, because every time we switch on and off that contactor, we're going to arc across those contacts. And that's, I mean, it's neither here nor there. One of the advantages of this type of switching, as opposed to a normal light switch, is it happens very quickly. We have the magnetic switch, the magnetic mechanical action in there that shuts the switch, and then when that magnet turns off, there's a big spring in there that pushes the two parts away from each other. So it happens quite fast, which minimizes the arcing. However, in saying that, the majority of the time when I've had to replace contacts is one of two things. One is that the coil has failed because it's just a little coil of wire, or number two, and probably more common to be honest, is that eventually the contact coils, the contacts themselves will corrode and fail due to arcing. It just happens. It is what it is. Life goes on. I mean, these things will last, we're talking probably 10 to 15 years of pretty heavy duty operation, opening and closing a few hundred times a day before they will burn out. They will burn out, but I mean, that's a long time and it's a lot of switching. What are you going to do? Okay, contact arrangements. Two types of contact arrangements. Changeover contacts comprise two separate contacts and one common contact that is activated. Double pole changeover contacts enable the polarity reversal of two conductors, which is often required in control circuits. For example, motor reversal and immediate switching in light circuits. Reversal's polarity is shown in the circuit diagram. The arrows show how the polarity is reversed with contacts in number one position. Yeah, so a changeover contact comprises two separate contacts and one common. So the common would be our single feed in. If we look at this diagram here, at just the top part there, that's just a normal changeover, right? So my power would come in and I'm either on one side or the other, one or two. Now if we were just using this to power a light or something, then we'd only have something connected off one. We don't need to worry about number two, but it's there. It's 1, 2. I can have something connected on 2 and something connected on 1. If we want this double pole changeover, for example, or what have we got here? So my output side there, the positive output will be connected to terminal 1 on the positive when we're in one position. When these two positions change over, it'll be connected to terminal 2 on the negative, and vice versa. So we're able to change our polarity if we need to. We can have time activated contacts. So normally our relay contacts operate really quickly, about 50 milliseconds. I don't know if that's true. I believe it. I've never got out with my stopwatch and measured how fast the relay will switch over. But sometimes we'll need a delay. So we have a timing relay which may be electromagnetic, pneumatic, or electronic. Yeah, we'll just take that for what it says. We can have relays with time delays in them. So once we stick power onto that relay, then it will start a countdown, and it will be whatever we set it to, or whatever it is set it to out of the factory, or whatever we set it to. Temperature activated contacts. Temperature control circuitry is necessary for heating equipment such as water, air, or process heaters. It may also be useful for thermal damage prevention in processes and machineries. To do this, temperature sensitive contacts are used and have a normally closed contact arrangement connected in series with the heating device or the control circuitry. Temperature sensitive contacts open, de-energizing the circuit when a predetermined temperature limit is reached. Well, that's fairly self-explanatory. If we had a temperature sensitive contact in series with the heating device, well, that's just a thermostat, isn't it? That when it reaches a certain temperature, it just opens, and the thermal thing is switching the load itself. The thermal contact is switching the load itself. In this drawing here, we have a thermal contact switching a relay coil, and then the relay coil will switch on a set of contacts which will switch the heating device or the load. Either one, yeah, that would be a temperature or thermostat relay or something like that, but they're not terribly common. Mechanically operated contacts. One of the most frequently used mechanically operated contact devices is the limit switch, wired in series with a control circuit. For example, the transverse movement of an overhead crane must have a mechanically operated electrical control to switch off the motor when the transverse limit point is reached. What does that mean? So a limit switch would be basically it's a stop switch. It's a stop switch, and it's going to be in series with our control circuit, in series with the coil. Remember that everything that we're doing in our control circuit is turning on and off, or turning on or off our coil, which the coil then switches the control contacts, or the main contacts rather, and that switches on the power to whatever the device is. In this case, it would be a motor, and that motor is controlling something that's moving. Yeah, an overhead crane. So we're talking about a crane that's mounted on a rail inside a workshop and go up and down. You have these in mechanics workshops commonly. They will move up and down, like as an up and down, and they can also run up and down the workshop, like along the workshop. And they'll be on a rail at the top. Now, you don't want that when that crane reaches the end of the rail at the end of the workshop, you don't want it to keep driving, because it's going to do some sort of damage, right? It's going to drive itself off the rail or through the wall, or it'll get stuck and it'll just grind away. So you have a limit switch there, and if you think of it at a very simple level, that limit switch would be like a button, a stop button. And so when the motor comes along, donk, pushes the stop button, and it stops the circuit. It's basically what a limit switch does. Direct online motor starter, semi-automatic. So what have we got here? This figure shows a semi-automatic version of a DOL starter. It is semi-automatic because it is started and stopped manually by push buttons. The diagram is in the vertical orientation, so our phase is coming in the top here. There it is, phase, and neutral at the bottom. Now remember, our contactor is a load here, so we can just connect our coil from phase to neutral. Just needs a neutral back, and all of the control circuits are in the phase between the supply and the coil itself. When the start button is pressed, all contacts are in the closed position, and the K1 coil is energized. The K1 contactor closes and the motor starts. The K1 auxiliary contact closes and maintains the circuit when the start button is released. Simple. That's exactly what we looked at before. I won't go through that operation again. If you think about it, we have a stop button in series, start button, the hold open contact is labeled K1 there, K1 hold open contact. That closes when the coil closes, which maintains the circuit even when the start button is released. Everything stays on until I push the stop button. That is called a direct online motor starter. That's the most common type of motor starter. We will do this. We will wire one of these up. Automatic DOL starter control circuits, 1 or 3 phase. A DOL starter may be automated by adding a hold relay. For example, in the case of a coal-fueled boiler that requires temperature control, a controlling thermostat is connected in series with the starter contactor coil, which supplies a coal hopper screw motor. When the temperature has reached the set point limit, the normally closed thermostat contact opens, de-energizing the motor starter coil. The motor stops and no more coal reaches the furnace until the temperature drops. When the start button is operated, the process will continue automatically until the stop button is operated. So what have we got here? We have got another relay here. So power comes down here, goes through the stop switch. I push the start button and power goes through. There's a little overload there. That's just an overload, like a circuit breaker, right? So that's always closed unless something goes wrong. It's just sitting there allowing power to go through. Power goes through here, through the little temperature contact, through the contactor, and back to neutral. This coil here will be holding on this contact here. This coil here will be powering the main contacts, and also, my bad, this coil here holds this on here. This here is just a thermostat. Okay, so how does it work? Power goes down here, I push the button on, This coil here turns on my main power, so the coal is being pumped into the fire. This coil here is activated, so that holds on this contact here. If the temperature gets hot enough, this will open, which will take the main contactor out, which means that no fuel is going into the fire. But the hold relay will stay on, which means this will stay on, so I've still got power up to my thermostat here. And then when the thermostat switches back on, it will switch my contactor back on, and my air heater goes back on. If I didn't have this relay here, that means every time this stops via the thermostat, I would have to manually restart that circuit. I have to go and push the start button again, which would be a pain, right? That's not ideal. So this is a automatic DOL. It still has the advantage of no voltage protection, right? So if I lose power here, if the fuse blows, for example, then both of these coils will shut down. So even when I replace this fuse, the process won't start again by itself. I replace the fuse, and then I'll have to push the start button to start it all again, and then it will resume automatic operation. Interlocking pairs of contactors. I'm not going to read this. I talked about on the video for the previous topic. I talked about interlocking pairs or interlocking contacts. This is where, particularly in motor reversing, forward and reverse, where we don't want. There's a possibility of a short circuit. It's a possibility of a short circuit if I have two contactors operating at the same time. So we will have the auxiliaries on each contactor wired in such a way that when one contactor is on, the other one can't be on, and vice versa. So even if I push the forward button and the reverse button together, when I switch one on, it's going to take power off the other one. So I physically cannot switch the other one on until I've switched the other one off. One day I will show you this stuff in the practical lab. I'll show you what I mean by that, and we can actually demonstrate it one day when the world is back to normal. What have we got here? Okay, here are our interlocks. This is a very simple demonstration of how an interlock works. So what we need to do here is pay very, very careful attention to the labeling here. On the reverse coil is labeled K2. This contact here is labeled K2. So that means this contact is being switched by this coil. And K1 is our forward. That coil is switching this contact here. One's normally open, normally closed. So if I put my switch in the forward position, I'll have power. That K1 will be on, and therefore this will be open. So both of these will be normally closed contacts. So as long as this coil is powered, this contact remains open. So I physically cannot turn that coil on. It can't happen because this will be off. When I switch this power back over to reverse, then K2 or K1 will de-energize, so that switch will close again. Power flows through here, turns on this coil, which opens this contact, which means I can't get power through to K1. That's the ideal scenario, right? I can't have power to K1 when I've got power on K2, can't have power to K2 when I've got power on K1. It's very simple. In very simple terms, that's how an interlock works. I'm going to take a moment here. I've told you that every test will have a code in it, and the codes will be embedded in the video. The code for this test for control circuits is going to be 4 digits. The first 2 digits will be 43. 43. I'm going to write that down so I don't forget it and have to go back and rewatch the bloody video. We're going to say control circuits, code 43 will be the first 2 digits. So when you go to jump into that test, it's going to be 43, and there'll be 2 more digits, which I will tell you at another time, either in this video or in the next video, depending on how I feel. We may go all the way through. Okay, mechanical interlock. So in the last slide here, so this slide we're talking about, this is an electrical interlock. Then the orientation of the switches means I can't provide power to the wrong contactor at the wrong time. So this would be a mechanical interlock. So we see here the two contactors. When one is closed, the other must be open. The physical contacts are linked together. So if I close one, I cannot close the other. As soon as I close the other, it's physically going to open the other. And yeah, I mean, that's all I can tell you. You look at the diagram there and you'll see when this one's open, this one must be closed, and vice versa. So they're mechanically interlocked, which means that there is a physical connection rather than an electrical connection, which is stopping that from happening. Alright, so relay control of power and lighting circuit. This is a simple diagram showing how power circuits are controlled by a control circuit, which is the whole point of this, right? So we have the control switch down here, or we can have a whole control circuit down in here with stop buttons, start buttons, so on and so forth. We have our coil. That coil switches these contacts here. So when the coil is energized, it pulls those contacts in, L1, L2, L3. We then have power off these three branches here, which might go to a motor or whatever. This again, this is how our stop button circuit, stop button circuit of 402 works. Down here where it says control switch, that's all our emergency stop buttons. They can kill power to this coil, and then off these wires here would be all of our sockets in that room. So when this is on, the sockets have power. When the coil is de-energized, all of these switches open and the sockets no longer have power. Simple. Understand? No, I didn't say yes to the screen. I know I can't hear you, but it'd be nice to imagine that you're nodding sagely, going, yes, I understand, I've got it. Two-way lighting circuits. Right, so we've seen interesting. So it looks like we're taking a hard left turn, and we're going to move away from contactors and relays, and we're going to two-way lighting switches. We've done two-way lighting switching. You all have physically wired that up. I would expect that if I stuck a two-way light switch in front of you guys right now today, you would struggle to wire that up. That's not the end of the world. It is what it is. Ultimately, it is quite a complicated concept, and at the end of the day, you know, I don't expect you to remember it. If I haven't wired one for a year, I would have to do a quick scribble, draw a little picture to make sure I knew what I was doing. You guys probably have zero recollection other than, oh yeah, I remember that I did that. A few of you might be able to figure that out, or look at this picture that we've got in front of us here and say, I remember now. But it is what it is. So look, well, I'll take this opportunity to stop this video. That will be the end of part 2. We will move on to part 3 shortly. I will have all of these uploaded to you by Thursday if you're watching this. Actually, that's an absolutely irrelevant thing to say, because whatever day you're watching this, it's obviously already been uploaded. Duh. Okay. Thank you. See you again soon.